Today we are going to do section 3.4, motion in space, on page 305. Now the motion, you might think that we're going to be talking about velocity and acceleration and such matters, and you are correct. See, the velocity is given by, first we have r of t, that's just the position. Okay, and velocity, as you might guess, is r prime of t. Acceleration is v prime of t, or r double prime of t. And to take the derivative of a vector, you just take the derivative of each component. And so basically you do it 3 times. And then the speed, you notice the speed is also called v of t. That v is not bold. Okay, and that's how we're going to distinguish the speed versus the vector. V, which is the velocity. Now the speed is the magnitude of the velocity, which is the magnitude of r prime, the derivative of r, and it also equals to ds by dt. And please remember all that stuff. I know there are a lot of different things that seem like same thing is called by different names and things like that, but they are, and so please keep it in some kind of a note and everything, so that you can keep everything straight, who's who and what's what. And then so the position, to look at it then, in 2D, the position vector is, as you might imagine, is x of t and y of t in 3 dimensions. There's a 3rd dimension, but otherwise nothing's different. Velocity is the derivatives of those things. Acceleration, the double derivative of those things. And finally, the speed is the Pythagoras theorem result of those things. In the 2D, you have 2 things squared added together. 3D, you have 3 things squared added together. But they work exactly the same way, except in 3D, of course, you have more work ahead of you. So having said that, please do example 3.14, which is just a repeat that we have done many times, and the motion along some parabola. Velocity, and go ahead and follow the formula. The formula is very, very straightforward, except that it's tedious, okay? And then, so having said that, let's go to the next page where we consider the acceleration vector. Now, let's look at page 308. Where we talk about the acceleration vector. The acceleration vector is given in component form in relation to the tangent vector and the normal vector. Now, before we prove this representation, which says acceleration vector is v prime of t, that's the tangent vector component, and then vt squared times kappa, and that's the normal component. But before we do that, let's remember the stuff, okay? What is v of t again? V of t is r prime of t. We just covered that. And the magnitude of v of t, then, of course, is the magnitude of r prime of t. A of t is v of t taking the derivative. And then the unit tangent vector is defined as r prime of t divided by the magnitude. We had that, I don't know, a section or 2 ago. N of t, excuse me, the normal, is defined as t prime divided by its magnitude. Okay, had that maybe last section or something. And finally, kappa, one of the kappa way to calculate kappa, it has several ways, right? But one of the ways calculating kappa is t prime divided by r prime. All this is we presented earlier, but I want to refresh you of the memory. So now that we know that, first what we're going to do is write down this equation. What is v of t? So v of t equals to looking at the equation that we already have. V of t is r prime of t, right? And then r prime of t is equal to, right here, is t of t times r prime t magnitude, okay? So v of t then equals to, going from here, t of t times r prime of t. I'll write that down. Which then we can rewrite this thing as, what is r prime of, what is this thing? That is small v of t. Now the one with a vector is the big V, okay? The one here is the small v. And this one here is actually the vector. So I should write that down. I only write down the vector notation for v because we have that small v here for the speed to distinguish the two. And so then we have that, and next we will plug in v of t as r prime of t here. So we'll write that down. V of t and then big T of t. And then that will give us this one equation. Now, and then the next step we're going to calculate what a of t is. Now, a of t, my marker is getting dim. Let me change it. So a of t, we're going to take the derivative of this thing, right? And so take the derivative of this side, and by the derivative laws, we'll take the derivative of the first one, which is v prime of t, and then times the thing itself, and then plus v of t, and the derivative of the second item, like this, the product rule for vectors, which looks very close to the product rule of non-vectors. And then so far we have that, okay, but we're still driving at the formula that's given. So the next step so far, we got the first part. See, this is the same as the first part of the formula, v prime of t times t. But now we just need to work on this part, which the formula that's given involves n. So let's look at n. Where's n again? N is right here. Now, being that n is this thing, right? So then that means t prime equals to n times the magnitude. So we write that down. Plug that in here. So the first one is the same, and then plus, what is that? T prime. All right, we will add it down. T prime is equal to v of t, and then magnitude t prime, and then n of t. That's coming from this thing right here. That what are we doing? Yeah, that we just substitute t prime as nt magnitude of this, right? And this is the same here. I will now copy that down. And then we have one more thing is plugging in the kappa. Here's our kappa, okay? So then kappa means that t prime, the magnitude of this thing is that times that. So we plug that in, so that equals to this thing here plus v of t, okay? The nt equals to, this thing right here, which is, sorry, what do I have? I forgot to put some magnitude line here. All right, so then we plug this thing, which is nt, which is magnitude, this one, which is, let's see, I'm confusing myself. Give me a second here. All right, I figured it out. Now we're focusing on kappa. And what is r prime of t? R prime of t is, is the same as v of t. Okay, remember that? Yes, r prime of t of v of t. So this is the same as this thing, v of t in magnitude. So this is the same as a small v of t, this part. Let's write that down. Okay, so then eventually, so t prime, the tangent vector prime of t is kappa times small v of t. So we'll write that down. We have this thing as v of t, okay, and then kappa times v of t, and that is in, yeah, and then n of t. So then it becomes kappa v primed, right? Kappa v squared, and that gives us the formula, which is the formula for the acceleration, okay, is v prime of t times the t of t, the tangent vector, plus v squared of t, the squared. Can the squared be there? No, let's not write it there. v of t squared, okay, times kappa times the normal t. So that gives us the quick equation. Now the proof involves remembering all the stuff, so it's better if you write it out so that it keeps it from being confusing. But once you write it out, the proof is actually, as you can see, extremely straightforward. Now that we have come up with this stuff, there are other ways to calculate this stuff as well. Now let's look at the next page, 309, theorem 3.8. The AT, the acceleration, can be represented as the tangent vector and the normal vector. Another way of doing it is this part is actually called A of t, okay? And so A of t, if A acceleration is written in the two components, then A of t, I guess I should write it down. I don't know why the book didn't write it down. Okay, so acceleration is A of t, okay, equals to AT. This is the vector, that's the component. It equals to let's see, AT, which is just a number of the t, all right, and plus an times n, where n is the normal vector. There's a t there, small t there. And then this is, so E equals to AT and AN, where AT is that thing and AN is that thing right here, the whole bit. Now another way of calculating this stuff, and which sometimes might make it easier, is that AT, that is this one, that's not a vector. AT is calculated as the vector A dot t. I'm talking about the dot product, okay? And which is also happens to be, how would you do that? Well, the t, we remember what we're talking about, right? What was t? T is r primed over its magnitude, which means that what is r prime? That's v, okay? In other words, it's the same as the a dot v, the a dot v being the velocity vector, divided by its magnitude, okay? That's the same as the unit tangent vector, and that's where we came up with this formula here. And so a lot of times this is much easier to do, I guess, than some other trick. And that's you can calculate the tangent vector with. Let's see, all right. And then another way of, so that's the AT part. And then next, AN is equal to, the cross product. Now to calculate AN in this case, what we're going to do is, let's look at a basic graph. Now here's the curve, the red line is the curve. And then we have AT, which is a tangent vector, which is going that way. A itself is going some other way, right? And then we need to calculate what AN. So we're going to use basic trigonometry here. So here's some angle theta. That's the angle between A and AT. Now, therefore, as a result, this length here, these are parallel lines. So this is also theta. Okay, and then we're trying to figure out the length of this thing, which is AN. AN is not a vector, it's just a number. So what is this? This would be let's see, this is the right angle. So this length AN will be given as A sine theta, right? Opposite, okay? So AN is the value of A, the vector A's magnitude times sine theta, where theta is this angle right here. Now, what is A sine theta? Let's write that down. So AN equals to A, the magnitude of the vector A, times sine of theta, which happens to be, now that's fine, but we also have some kind of a cross product happening here. Now the cross product of V cross A happens to be, see, V cross A, there's a formula that says V V is a velocity vector. Anyway, V cross A equals to VA sine theta, okay? That's one of the formulas for the cross product. So therefore, if you divide the magnitude of V out, then AN, which is A sine theta, is just V cross A magnitude divided by V, see? And that will be equal to, so that's where we got this part, is that this is V cross A and divided by V, by the magnitude of V, and that is, that's exactly the AN, okay? So that's one way to do it. Another way of doing it is we just look at the triangle again and calculate AN by the Pythagoras theorem. Now so we're trying to figure out the length of this. And if we already know how long A is, okay, and then we also know how long AT is, right? We'll just use the Pythagoras theorem, right angle. And so then AN is equal to A squared magnitude subtracted by AT squared magnitude. And then you take the square root, and that's where that is. And that's where the second formula in your book comes in. See, AN also equal the square root of the hypotenuse squared minus one side squared, and being the AN is the other side of the right angle triangle. So that's how theorem 3.8 is demonstrated. Having said that, please do example 3.15 as part of your homework. The actual application of these things are very, very simple. I mean, very straightforward. It's not like, although can be very tedious, as I can see here. You got to take the square root and square it and all that stuff. But it's just, well, it's still just algebra, tedious algebra that might take a while. So please do example 3.15 as part of your homework. And next, let's look at projectile motion. The projectile motion is the same thing we've done in Calculus 1 and maybe even Calculus 2, like what, I would say 5 times, 5 different times of doing the exact same thing. And here is nothing's different, okay? That is, everything is done with vectors, but we're still doing only 2-dimensional projectiles. That is, there's no wind, crosswind. If there's a crosswind, so we have a 3rd dimension, then I'm more interested. But being that this is just a repeat of what we've done many, many times, please look through this stuff yourself, okay? And it should bring back pleasant memories of Calculus 1. And then do example 3.16. Just for the heck of it. Is similar to what we've done many times, but you know, you shoot stuff up at an angle so it follows a parabola. If you remember that. And anyway, so do that as part of your homework. It looks somewhat tedious. All right. And then the book even tried to calculate what is the maximum distance. I think even that we did in Calculus 1 for the derivatives. So yeah, go ahead and look at that as well. Which angle you should shoot to get your stuff to fly the farthest, but that is we've been there, done that. So so please do example 3.16 and also look through the section a little bit as part of your homework.